How do we turn salt water into life-giving fresh water? The answer is reverse osmosis. This advanced technology is revolutionizing water purification and desalination across the globe. Under high pressure, water is forced through a semi-permeable membrane. This membrane allows pure water molecules to pass through, while rejecting salt ions and contaminants. Result: pure, safe drinking water. Reverse osmosis. Essential for our water future.
Welcome to This Explainer. Today, we're jumping right into the raw data behind, well, one of the most critical engineering processes on the planet. We're talking about turning salt water into fresh water using high pressure and semi-permeable membranes. I absolutely love unpacking these kinds of data sets because it really shows us exactly how theoretical chemistry becomes real, measurable engineering. So to set the stage here, how exactly do we turn salt water into life-giving fresh water? The answer is reverse osmosis. Basically, this process relies on incredibly high pressure, forcing water through a semi-permeable membrane. Think of this membrane as the ultimate gatekeeper. It lets those pure water molecules pass right through, but it aggressively rejects salt ions and other contaminants. The stakes are massive here, guys. Reverse osmosis is absolutely essential for our global water future. Section 1. Calculating membrane raw flux. Let's transition from the physical process over to the actual mathematical foundation that engineers use to measure it. Now, to measure performance, we use what's called flux, or J. This is essentially the rate at which pure water pushes through the membrane. The formula itself is pretty simple. J equals 1 divided by the membrane area, that's A, multiplied by the change in volume over time. In the practical session we're looking at today, our membrane area is exactly 0.024 square meters. Looking at the FTO1 TTO1 dataset, you can really see the math come alive. The formula takes raw differential pressure, which ranges from 10 to 30 bar, and converts it into raw flux, and eventually into calculated membrane resistance, or RM. For example, at a high pressure of 30 bar, we generate a really high raw flux of 14.792 liters per square meter per minute. It's just a perfect step-by-step mathematical conversion. Section 2, determining membrane resistance. Because fast-flowing water is really only half the story, right? We also need to analyze how the membrane physically pushes back. When we plot permeate flux against the applied differential pressure, it reveals this beautiful linear correlation. Down at 10 bar, our flux is just 4.58. But if we crank that pressure up to 30 bar, the flux climbs all the way to 14.79. Simply put, the harder we push, the faster the clean water flows. The real secret behind that data is the trendline equation. J equals 0.5125 times dP minus 0.7083. Now, why does that matter? Because that slope, the 0.5125, gives us the specific resistance characteristic of the RO membrane, known as Rm. It's essentially the precise mathematical baseline for the membrane's natural physical pushback. Moving on to Section 3, analyzing salt rejection rates. Because, let's face it, fast-flowing water is completely useless if it's still salty. We have to look at the system's salt rejection capabilities. We actually measure separation efficiency using electrical conductivity. Rejection, or R, is calculated by taking the feed conductivity, which is basically the saltiness of the input water, subtracting the clean permeate conductivity, dividing that by the initial feed, and then multiplying by 100. This percentage tells us exactly how much salt was successfully blocked. The results here are super interesting. We see a massive efficiency spike right in the middle. The highest salt rejection hits exactly at 20 bar, reaching 58.28%. If we drop the pressure to 10 bar, rejection plummets to only 23.57%. But here's the crazy part. If we push harder, say to 25 or 30 bar, the rejection actually plateaus and then drops. So the membrane hits its absolute optimum separation performance at exactly 20 bar. More pressure definitely does not always equal better purification. Section 4, normalizing flux for temperature. To ensure our data modeling is totally accurate, we have to account for physical variables like temperature, which directly affect water's permeability. It makes sense, right? As water gets warmer, it flows easier, which can artificially inflate our flux numbers. So we contrast raw flux against a normalized metric called J25. By applying an exponential correction formula, we can adjust all the data points as if they were tested at a standard 25 degrees Celsius. It basically removes temperature as a misleading variable. Comparing the raw and normalized flux side by side really confirms our data integrity. Across all feed pressures, the normalized J25 flux is just slightly lower than the raw JT flux, but it maintains the exact same trend lines. This proves that temperature only had a really minor effect in this specific experiment, which is great because it allows for a completely fair comparison across different feed pressures. Finally, Section 5, AI and industrial engineering. Let's zoom out from these precise manual calculations to the macro view of industrial processing, where the scale is just massively different. This is where the incredible value of AI in industrial engineering really shines. AI and digital tools take the exact same mathematical logic we just walked through, like calculating that J trend line or finding that absolute perfect 20 bar sweet spot for salt rejection, and they scale it infinitely. Instead of humans plotting a few data points after an experiment, digital tools process these complex flow rates and resistance variables instantly, live, right there on the factory floor. They give us real-time predictive modeling. That means the system can automatically adjust pressure to maintain optimum separation efficiency, no matter how much the feed temperatures fluctuate. It's a total game changer. So think about this. With digital intelligence instantly optimizing every single micro adjustment in pressure and flow rate based on this math, how will AI redefine the ultimate limits of industrial separation? Will we push reverse osmosis beyond what we currently even consider mathematically optimal? It's wild to think about. Thanks so much for joining me for this explainer. I really hope you walk away with a much clearer understanding of the raw data that's driving our pure water future.